This is a brief tutorial or review of hybridization and atomic orbitals. So let's just take a look at this first picture. We have here the different orbitals. This is orbital notation. So you've got the 1s2 and right there, and then it comes up to 2s2 and 2p2. So this is obviously carbon. So this is in the ground state. And then what happens is that you promote one of the electrons up to that p, sort of an excited state. So when it goes into bonding, it gets into an excited state. 1s stays the same. It's exactly the same. But now we've got 4 empty orbitals that carbon can use to bond. So if we, move this one out of the way, and let's come to the next picture. And it's kind of another way of looking at it, but you can see now, so that was just carbon. Now carbon, we've got some hydrogens. And so what happens is, again, that one electron gets promoted up here, so you get this excited state, and you have the 4 hydrogens. They're just hanging out. They only have 1 electron in their 1s orbital. So now after hybridization, instead of there being s and p, they call them sp. Each orbital is an sp, what they call sp3, because all 3 of the p orbitals are involved, and they're each going to bond. So each one of these is going to bond with a hydrogen to get 2 electrons in each orbital. And this is all about bonding. You want to get the full octet. You want to be stable, right? So what that means is then to become stable, you end up with this. And you have these, I mentioned before, the sigma bonds. And that's a single bond. The hydrogen here bonds with the carbon. Okay, so carbon is forming one bond here. And you'll notice that there's these little tails out in the back. I'm going to show you what that means in just a second. But the H is each bond, and a sigma bond with one of the carbon's electrons, right? So it has an sp3. Each orbital is exactly the same. Hybridization means that every orbital is the same. So I'm going to actually make this just a little bit smaller and push it up here. And we're actually going to cover the title up for a second. And we're going to move this picture out. I might as well just... I'm going to have to make that one smaller. Okay. Okay. So what's happening is that when the S combines with each one of the P's, you get the sp3. And you can see that each orbital is exactly the same. So that when you get this combination, you know, the way that I draw it sometimes, the way I talk about it is that there's 4 different distinct orbitals, but they're separate, but they are the same shape. See, they've got the little tail there, which is what we were talking about up here. So if you have a carbon with 4 hydrogens, there are 4 of these sp3 orbitals. Okay, so let me give you some examples about what that might look like. So I'm going to make these small again and get them out of the way. And let's do some drawing. For example, BeCl2. So you have a beryllium in the center. This is one of the electron deficient species that, of course, is linear. By the way, you guys really need to know those. You really need to know all your shapes. So linear, and so you've got 2 bonds. Okay, since you only have 2, that's 2 SPs, but what they would call that is an sp2. Or I'm sorry, this is just 2. I'm sorry, just 2 of these bond together, so it's an S and a P. So because there's an S and P, each one being equal, that means that there's an SP on this side and an SP on this side. Now the way I counted up is that I always just do like this, P, P, P. And so there's 2, so there's 1 here, so blank stuff here, that's why each one's an SP. Okay, but let's say we had BF3. Then we have a boron in the center. Again, this is an electron deficient species. And here's a fluorine, there's a fluorine. Okay, and so now for this one, let me get my eraser out. And what we can say is that, oops, I'm not doing very good, it doesn't matter. So we have 3 bonds, so it involves 1s and 2 p's. Each of them are identical, which means each one of these is an sp2. sp2, sp2. So there's 3 sp2 bonds. Okay? So now I'm going to make this smaller for a second, and let's do an entirely different one. And we're talking about the sp3s for a second because you have different versions of this, and I want you to know what's all possible. The standard one that we're all very familiar with is let's do over here, CH4. Remember, we have SPPP. Okay, and so we have carbon in the center, and we have our 4 hydrogens. Now there are 4 things on the central carbon, spp. We're going to involve all of these different orbitals, so all of them are sp3. Makes sense? Okay. What if we have an NH3? Okay, we have a nitrogen here, and we have an H, H, and an H. So you might say, oh, there's only a double, or I'm sorry, didn't mean to make that. Double bond right there. Okay, there's only an atomic orbital up there, and so if there's only, there's only a lone pair up there, so it shouldn't be involved, but it is involved. This is still an sp3 because there are 4 things on the central atom. You count the things. It could be a double bond, it could be a lone pair, doesn't matter. It's still one of the things, and so the orbitals are still used. So each one of these are sp3. Okay, same thing for H2O. Okay, so you have an O in the center, you have an H here, you have an H here, double bond, lone pair, still, all of them are sp3. Okay, that's what each of them represent. So that's pretty much what hybridization atomic orbitals is. So hopefully you can, whatever it is around the central atom, you're not doing it around the terminal atoms or on the outside, it's whatever's in the central atom. And that's all. Thanks.